Welcome to today's paper reading. Today's paper is titled, GaLore, Memory Efficient LLM Training by Gradient Low Rank Projection. This paper, titled GaLore, Memory Efficient LLM Training by Gradient Low Rank Projection, was published in the Proceedings of the 41st International Conference on Machine Learning by Jiawei, Zhao and colleagues from California Institute of Technology, Meta AI, University of Texas at Austin, and Carnegie Mellon University. The training of large language models, LLMs, faces significant memory challenges, primarily due to the increasing size of model weights and optimizer states. Common memory reduction techniques, such as low-rank adaptation, LoRA, add a low-rank matrix to frozen weights but often underperform compared to full-rank training. In this work, the authors propose gradient low-rank projection, GaLore, a strategy that enables full parameter learning while being more memory efficient than traditional low-rank methods. GaLore reduces memory usage by up to 65.5% in optimizer states and maintains efficiency and performance during pre-training on llama models and fine-tuning on GLE tasks. Additionally, 8-bit GaLore further reduces optimizer memory by up to 82.5% and total training memory by 63.3% compared to a BF16 baseline. This approach allows for the pre-training of a 7B model on consumer GPUs with 24 GB memory without the need for model parallel, checkpointing, or offloading strategies. Large language models, LLMs, exhibit remarkable performance across various domains, yet their pre-training and fine-tuning processes are computationally and memory-intensive. These processes necessitate not only a vast amount of computation but also significant memory, encompassing billions of trainable parameters, their gradients, and optimizer states. For instance, pre-training a Llama 7B model demands at least 58 GB of memory, rendering it impractical on consumer-grade GPUs like the NVIDIA RTX 4090. To address these challenges, the authors propose gradient low-rank projection, GaLore, a strategy that enables full parameter learning while being more memory efficient than traditional low-rank adaptation methods. GaLore leverages the low-rank structure of the gradient matrix, significantly reducing the memory cost of optimizer states and achieving up to 30% memory reduction compared to LoRA during pre-training. This approach allows for the training of large models like Llama 7B on a single GPU with 24 GB memory, without the need for costly memory offloading techniques. Figure 1 illustrates the estimated memory consumption for pre-training a Llama 7B model with a token batch size of 256 on a single device. The figure highlights the memory requirements without the use of activation checkpointing and memory offloading strategies. This setup is crucial for understanding the feasibility of training large language models on consumer-grade GPUs with limited memory. The details of the memory breakdown and the impact of different optimization techniques are discussed in section 5.5. In the related work section, the focus is on several key areas. Firstly, low-rank adaptation, LoRA, was proposed by Hu et al. In 2022 to fine-tune pre-trained models with low-rank adapters, reducing memory footprint. Variants of LoRA have been developed to enhance performance, support multitask learning, and further reduce memory usage. Secondly, subspace learning has shown that learning primarily occurs within a low-dimensional parameter subspace, which is utilized in metalearning and continual learning. Lastly, GaLore is related to projected gradient descent, PGD, but it considers the specific gradient form in neural networks, which has a matrix structure, unlike traditional PGD that treats the objective as a general black box function. GaLore is a strategy that leverages the low-rank structure of gradients to reduce memory consumption during training. By maintaining the gradient statistics of a small core of the gradient, rather than the entire gradient, significant memory savings can be achieved. This approach ensures that the training dynamics remain unchanged. The low-rank property of gradients is established through theoretical analysis, showing that under certain conditions, the gradient becomes low-rank during training. This is particularly relevant for large batch sizes and specific network architectures. The convergence of GaLore is proven under a generalized gradient update rule, and the choice of projection matrices P and Q is crucial for faster convergence and reduced memory usage. Unlike LoRA, GaLore does not introduce additional low-rank adapters, maintaining the original training trajectory when the rank is maximized. GaLore enables memory-efficient training by switching across low-rank subspaces. This involves recomputing projection matrices point and QT at regular intervals, allowing the algorithm to learn full-rank weights without increasing memory usage. The method significantly reduces the memory footprint of gradient statistics, particularly beneficial for optimizers like Atom. GaLore introduces additional hyperparameters such as the rank R, subspace change frequency T, and scale factor alpha, which control the strength of the low-rank updates. These techniques collectively contribute to a more efficient training process, especially for large-scale models like LLMs. Figure 2 illustrates the process of learning through low-rank subspaces using GaLore. Initially, weights W are updated by projected gradients GT1 within a subspace defined by fixed matrices point 1 and QT1 for T1 steps ranging from 0 to T1-1. After T1 steps, the subspace is altered by recalculating point 2 and QT2 for the subsequent steps T2 in the range, T1, T2-1. This cycle of subspace switching and weight updates continues until the model converges, effectively traversing through multiple low-rank subspaces to optimize the weights. In this section, we evaluate GaLore's performance in both pre-training and fine-tuning scenarios. For pre-training, we apply GaLore to train LLM-based models on the C4 dataset, ranging from 60 million to 7 billion parameters. We report validation perplexity and compare GaLore's memory efficiency with other low-rank methods such as full-rank, LoRA, and LoRA. GaLore demonstrates significant memory savings while maintaining competitive performance. Additionally, we fine-tune pre-trained models on GLE tasks to assess GaLore's effectiveness in memory-efficient fine-tuning. GaLore outperforms LoRA in several tasks, indicating its potential as a comprehensive memory-efficient training strategy for large language models. Figure 3 illustrates the application of GaLore to different optimizers during the pre-training of a Llama 1B model on the C4 dataset over 10K steps. The graph shows the validation perplexity for each optimizer, with GaLore being applied at ranks 512 and 1024, corresponding to the model's dimension of 2048. This setup allows for a comparative analysis of GaLore's performance across various optimization strategies, highlighting its adaptability and effectiveness in reducing perplexity. Table 2 presents a comparison of low-rank algorithms in pre-training various sizes of Llama models on the C4 dataset. It reports validation perplexity and provides memory estimates for the total of parameters and optimizer states based on BF16 format. The table highlights the performance of GaLore against full-rank and other low-rank methods, showing its efficiency in terms of memory usage and comparable performance in validation perplexity. The actual memory footprint of GaLore is detailed in Figure 4. Table 3 presents the results of pre-training the Llama 7B model on the C4 dataset for 150K steps. The table reports the validation perplexity and memory estimates for two methods, 8-bit GaLore and 8-bit Atom. The validation perplexity is measured at different training steps, 40K, 80K, 120K, 150K, and the memory estimates are provided for each method. Additionally, the table includes the number of tokens processed at each training step, which is crucial for understanding the model's performance and resource utilization during pre-training. Figure 4 illustrates the memory usage for various methods across different model sizes, specifically evaluated with a token batch size of 256. Notably, 8-bit GaLore with retained gradients demonstrates a significant reduction in memory requirements by disabling per-layer weight updates, but storing weight gradients during training. This method is compared against the BF16 baseline, showing its efficiency in memory management. The impact of per-GPU token batch size on memory usage is also highlighted, indicating that even with smaller batch sizes, the memory footprint remains manageable, especially when activation checkpointing is enabled. Table 4 evaluates GaLore's performance in memory-efficient fine-tuning on the GLUE benchmark using pre-trained RoBRTA-based models. It reports the average scores across all tasks. Key findings include GaLore's superior performance over LoRA on most tasks, with notable memory usage differences such as GaLore, rank equals 4, using 253M memory compared to LoRA, rank equals 4, using 257M. Additionally, the average scores highlight GaLore, rank equals 8, achieving 91.11, slightly below LoRA, rank equals 8, at 91.22. In this ablation study, the authors investigate the optimal frequency of subspace updates during pre-training. They find that both too frequent and too slow changes of subspaces negatively impact the convergence of the model, as illustrated in Figure 5, left. For smaller values of R, more frequent subspace switching is necessary to prevent optimization steps from being wasted in incorrect subspaces. Conversely, for larger values of R, the gradient updates span more subspaces, providing a buffer effect. This study also demonstrates that GaLore can be adjusted to balance memory usage and computational costs. In memory-constrained scenarios, reducing the subspace rank allows for longer training iterations within the memory budget, thereby preserving model performance. Figure 5 presents an ablation study of GaLore on 130M models, focusing on two key aspects: the impact of varying subspace update frequency T and the effect of varying subspace rank in training iterations. On the left, the study examines how different frequencies of subspace changes affect the convergence of the model. It shows that both very frequent and very slow subspace changes can negatively impact convergence. On the right, the study investigates the relationship between the rank of the subspace and the number of training iterations, demonstrating that within a certain range of rank values, decreasing the rank only slightly affects the convergence rate. In this paper, the authors propose GaLore, a strategy that significantly reduces memory usage during the pre-training and fine-tuning of large language models. GaLore achieves a reduction of up to 65.5% in optimizer state's memory usage while maintaining both efficiency and performance. The authors also identify several open problems for future research, including applying GaLore to other types of models like vision transformers and diffusion models, further enhancing memory efficiency, and exploring the feasibility of elastic data distributed training on consumer-grade hardware. Additionally, the paper highlights the environmental impact of their work, aiming to reduce the carbon footprint associated with training large models. The authors acknowledge the support from various organizations and individuals, including Meta AI, Florian Schaefer, Jeremy Bernstein, Vladislav Lyalin, and NSF Awards. Thank you for watching.